Okay, it's all set up. Hello everyone, it's been a while since we met, I think. It's been, last year. Yeah. I was just thinking about what I should do today, and I realized that we can talk about Mujoco, kind of, and some reinforcement learning, but I found that like this pre-exam time when we have tests and stuff like that, it's quite hard to do some things in parallel. So I'm not sure if it's gonna be like extremely good explanation, but I try to get into the details as much as I can explaining this. So I think it's gonna be all right. And also, about the organizational question that will at February. I don't think we will be meeting because all of us have exams, and I'll not have time for this. You will not have time for this. So yeah, okay. Let's get the ball rolling. So Mujoco, why not gazebo? I found it in a hard way, so I tried to do some reinforcement learning in gazebo, which is impossible, unfortunately. It's not just optimized; it doesn't have those qualities that it should have. So I found that I did some research by asking Gemini what is better. So it supposed me that Mujoco is better. So I'm just gonna read that information for you real quick. So Mujoco is a robotic simulator developed by Amo Todorov of the University of Washington. It's maintained by some blah blah blah. Mujoco multi-joint contact of the current simulation options. I've found that Mujoco is the easiest to use and demands at least computational power. Yeah, and that's also a very important thing. Why we should use that, because it's very good for the reinforcement learning, because it's very efficient and it's not that demanding on the hardware. For example, I changed my Windows laptop to the Ubuntu eventually, so I could run some things, and it works pretty okay. Not the best, but I mean, it works. And this is like 2017 graphics card, so it's pretty good optimized. So okay, here's the hard stuff going. Okay, so what I actually have you to have something to show to you today is, oh wait, yeah, and I'm actually doing the recording. Okay, so because I need to set up some things. So today we are gonna see how reinforcement learning is working. I'm gonna dive into the details as much as I can, and how to establish like reinforcement learning and try to learn some robot to do some things in reinforcement using reinforcement learning. So okay, let's do something like, okay, I need to set up something. Does everybody knows what is conda? Because I'm not sure. Oh, it's visible. Maybe somebody knows. Somebody doesn't. Okay, somebody doesn't. Can you explain what is conda?
So it is like, how to say it? It is used to set up a Python environment.
Yeah.
So we can have multiple separate environments with different settings and different packages versions, so they don't follow.
Yeah. For example, if you have a laptop and you just download all of the libraries on your laptop, it's gonna be like so much memory used, and you need to like deal with that, and it's quite hard. So we just establish some virtual environment, like a separated space where we'll install our libraries that we need, So I have already created some environment where I installed all the things that I need for this presentation today. So okay, I'm just gonna at first I'm gonna run it. As time goes by, as I explain, you will see the difference, how it learns. So at the end you will see probably something working, hopefully. I'm just gonna check a few details. Okay. Is it okay? I need to make it larger, I think. Okay, good enough. Okay, so we are using. Okay, let's take a look at the include. What have you got? Okay, what is this? Okay, no. At first we need to run. Yeah. Yeah. So at the end we will. The thing is called inverted pendulum, if I'm correct. Yeah, inverted pendulum, and the problem is with making it move. Like you probably saw it somewhere, or like it's there's very popular library and video of this pendulum in 2D trying to learn, but this time we introduced some physics and we try to do it as we would do it in the real robot. So it's completely like physics included simulation. So okay, let's just close it a bit for now and just take a look what we've got here.
What's the program supposed to do?
We will teach the inverted pendulum because it's like a base that's moving, and we have like a wiggling stick, and when the base moves, the thing starts to fall. So our problem is that we want to make the stick stand, so we need to move it like this, and we will try to teach our neural network how to do that by using some algorithms, joining algorithms, but more than that as we go. So we have some NumPy, pandas, Torch, which can like NumPy for working with matrices, pandas for data science, I guess, Torch to work with neural network, and we have the Gymnasium. Actually, Gymnasium, it's I think it's an OpenAI library. It gives us the possibility of just simply run the code without any kind of extremely heavy preparation with downloading some models, making the matrices that describe the how is it called, the physical movement of the our model, like how should it move in the real world. It's all predefined there. There are like few models that have those things predefined. So for the sake of simplicity, I use that. Okay, let's start. So, okay, this is not important. First of all, we have our class defined called policy network, which is, if you remember the loop that I want to write something. We don't have a marker. That's a problem. Maybe someone has extra marker by chance?
Or a whiteboard? No.
Okay, I'm just gonna check this room and maybe they have. Okay, I got it. So we have our policy network. So we are using deep learning here. I haven't in the presentation included what are the differences in reinforcement learning and deep reinforcement learning, but simply is our agent in the deep reinforcement learning is some kind of like neural network which takes some inputs and gives us outputs, and we don't really know what's going on. In regular reinforcement learning, like Q learning, we just have a lookup table. More on that later. So we have our matrix defined. We have those entry points, which is observation space dimension and action space dimensions. If you remember, when we try to teach from the last reinforcement learning lecture that I gave, we need to teach our agent based on the environment to do some actions. So we include some observation nodes here at the start of our neural network, which describes the environment it is in. So and we have as you can see here, we have some kind of amount of them. I don't know, like it depends actually. I don't remember what was the number, but we get it from our environment. It's not that important. So this is the observations. I'm gonna check the time. Okay. So the next layer we have is 16 layer linear neural network layer. So we have like 16 nodes here, which are all interconnected. I think I don't need to write all of them like that. Yeah, okay. And we have 16 of those. So next layer is this one, which is just takes the tangent of our weight of our node, which is described here. So this is tan, which is like this everywhere. Okay, I'm not sure if it's in every kind of.
Hyperbolic tangent, right?
Sorry, is it just
Is
a
it
tape?
hyperbolic or normal? Is it the hyperbolic tangent or normal tangent? Because over there it's like tan h.
I'm not sure. It's like this. From the
So the hyperbolic.
yeah, the hyperbolic. Okay. Does they differ a lot? Because I'm not.
Yeah, so basically like hyperbolic tangent is like that, and tangent is like that.
Ah, okay.
Yes.
Okay, so we have the hyperbolic. Okay, so we have tan h. So all of our values we got in the second layer, they are all going through the tangent, and then we have another linear, which so we have 16 nodes here, like 16 of them here. Then we are going with them to the 32 layer, with this 32 nodes layer. We have like 1, 2, 3, blah 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 blah. There are 32 of them. It's just the definition of our neural network is not that important. We could use whatever we want. We could use 2, 3, whatever. Just in this tutorial we use like 16, 32. You can use whatever you want. Okay, so next one is also tangent. And so on, yeah. Okay, not that important. In our shared network. Then we have the policy mean network, which is taking our, because from now on we went from the observation space to the 32 layer and tangent, as you can see here. This is our shared network defined here. Next one is the policy mean. We just take the same thing and we put it through the we just make a we use a linear function from torch to make it go from 32 values, so there's also like 32 values of those, to the action space. And actually, here comes the interesting thing. Like there are 32 nodes. Wait, nodes, right? Okay. And yeah, action space. And those are two values our neural network bases on when it makes the decision. More on that in a minute. Then we have some forward function defined. We have the same thing defined, just because we will see it here. Not that important. So policy means specifically near layer. So okay. Okay, I don't have a connection to the Wi-Fi. We have the okay, so this is the basically okay, it's this is the action which is taken. So we have our policy network, our neural network, our agent. So we have a policy, we have some kind of action that we are trying to take, and we have the state T or whatever, which are we in making this decision. So basically our action is just chosen from the distribution of the actions. What I'm trying to say, here we have the norm, the mean value of our distribution, and the standard deviation. So if you had the statistics in the university course, so you know what it is. So if we have some action space, and we just plot them, it will, as we learn our neural network, it becomes like, depending on the state we are, it takes some actions. So basically, this is the mean value of our normal distribution, and we have some standard deviation included here. So this is the probability. The probability of taking some kind of action. For example, in this point, the action is taken, it's some kind of 1 or whatever the value we choose. So, and this is basically what means the deep learning continuous actions. We don't have discrete actions. We have them like continuously infinite amount of actions. It goes like to the infinity. So, but we don't choose from all of them. We just choose some from this area which are close. And basically, when we learn, this is important. When we teach our neural network like that, it becomes like, because at the start, it doesn't look like this. It looks maybe okay, not like that. It looks maybe something like this. So we don't know like the obvious solution. as we iterate through our neural network, it gets smarter. So it starts looking like a bell. For example, at the, I don't know, whatever, 30th iteration, it will maybe look something like this. But it's still not obvious. At the, I don't know, 100th iteration, it will look like this. So, and it's gonna be wider and wider. So the action we are taking is gonna be more probable because we have the probability here. And our model will generally take much more like correct actions. Is that more or less understandable? Okay. And we also have some discrete actions. It's not the, you know, they're just, you know, 1, 2, 3, 4. We don't have like this kind of Cartesian space when we define all of the actions we could take. They are just discrete actions, 1 or 0, left or right, and stuff like that. We don't care too much about it in this case because we have like harder problems. In harder problems, we probably use the continuous action space because our robot has the actuator, and it has the, you know, it can be in so many positions. If you include them in some kind of lookup table and try to predict what it will do in the future, it's going to become so messy. So these is just a continuous action space. So we take some, yeah, and okay, and so yeah, we saw that. I think I explained this part of its neural network. Let's dive into the code. I'm just gonna try to make it bigger. Okay. Maybe I can. No. Okay. So we are defining one neural network here for defining our action space, and basically the same one. You will see why. I have the further forward function here. So condition on the observation returns the mean and standard deviation of a normal distribution from which an action is sampled from. So, and basically when we have this distribution, how do you think we will take some action and evaluate it? We just take some sample, for example. Okay, let me write something normal here because it looks like craziness. We have our some Gaussian distribution, let's call it that way. We have some value here, which is mean, and we have some standard deviation, maybe here. This is standard deviation describes, so imagine if you're taking an integral over all of this space under this function. This is the 100%. The standard deviation, it includes like 95% here because all of that thing here is like so small amount of space. So it's like summing up those things. It's going to be 2.5% here of all of the volume here and 2.5% here. So we're just taking within those limits. We're taking some other actions. So. Well, when we take some action, we just, you know, try something out. It's more likely to be here because we have the probability a little larger here. But for example, it can happen here, it can happen here, it can happen here. So we choose different actions. So we just sample them. Okay, we have some observation from the environment including the function. It returns the predicted mean of the normal distribution and standard deviation of the normal distribution. So mean is this thing and the standard deviation is this thing. It just predicts in those two nodes, in those two values, which are, So we start from the observation and we end up in some kind of, plot when we can sample our action from. So next thing, building an agent. Now that we are done building the policy, let us develop reinforced. So basically, and the main problem here with those policies is how you train them and what algorithm you use to, because all of those to change the weights of our neural network, all of those nodes, they have some values, and this means some of those plus some bias and stuff like that. So all of them affect each other. So we need to change them. For example, if we take wrong decision, our environment, which we are affecting on, like for example, if I move our pendulum like this, it's a bad thing. So the environment gives us the reward, which is bad, which makes our neural network like think, the last function is big because it actually depends how we define the last function. Okay, whatever. So if we do a bad thing in our environment, this neural network changes. How it's changing? Changes using the gradient descent. I'm actually diving very into the details here, but yeah, I don't know. Are you okay with that? Because I see that's. I mean, it's not that exciting, but what can I do? That's what I could learn about this reinforcement learning and robotics. I was just generally trying to find some connection between robotics and reinforcement learning. That's what I found, and I found how it can be used. So there's this course called reinforced algorithm. I have the presentation somewhere here. Yeah. Okay. Oh, so this is our thing that I showed. Basically the exact same thing. Probability, probability, the mean, the action, stuff like that. Okay, so our about reinforce. So the main problem right now, when we define our neural network, is how we change the weights. Reinforce is the algorithm which is based on some response from our environment, changes the values of our neural network, the weights, so it takes better actions in the future. And generally we have a lot of algorithms like that, like PPO, SAG, DDPG. Maybe you heard of them. I don't know, because I didn't before today. It's what we use to update our omega. Omega is generally, I don't know, in some publications, if you read them, omega is just simply the definition of all of our weights and biases. Like imagine a vector of our, or a matrix of our weights and biases. It's just a general simplification. So here is the loss function, and we're gonna see how it's defined in the code. So we have our, okay, so think of this like an, I might write it down for better illustration. It actually differs from the implementation this formula, but it generally is similar. Okay. So as I told you before, this is how our neural network learns. We have old, this is the old weights and biases, and to make new ones, we just do the gradiated descent. This stands for gradiated descent. I'm gonna show you in the code how it's implemented, and we do some logarithm of the probability of this action, of some action that was chosen happened in some kind of state, multiplied by g of t. G of t is our reward function, the one I told you that we need to get something from the environment to understand, like, is it true, is it bad, or whatever we should do. So this is basically the loss function, right? And there are different writings of this thing. It can be with minus, it can be with plus, because it actually depends on how you implement them. And I found this thing. It was without the multiplication by the reward, but I mean, I just added that. Maybe there's someone using something like this reinforced algorithm without the g of t, our reward function. So, okay, let's keep going. How much? Okay, okay, so we have some arguments also in our reinforced algorithm, because it also takes into account our observation space and actions. So we are defining our learning rate, how fast our gradient is descending, what steps it makes, and we have some discount factor which is included in our g of t. I'm gonna just real quick. I didn't include. Okay, here it is. We have some. This is our first reward plus some gamma plus second reward plus gamma squared plus multiplied by reward from the next frame. And this is reward 1. Oh, no, t plus 1. Okay, t plus 2. Okay, and it goes so on. So our gamma can be from it's usually from 0.9 to 0.999. What it actually means when we define our, so first, when we have some defined environment, for example, I don't know if it's going to be shown here good. It's going to be good. Okay. And as you can see, it learned a bit. Yeah. So I just forgot the vocabulary for this. So the episode, okay. In the episode, we have few actions taken. For example, this is the end of the episode. This is the end of the episode. This is the end of the episode. So we have like few episodes going on, and in every episode we have some actions that is moving right, left, and wherever. So, and for every action, we are calculating the reward. So in one episode, we are having few rewards. And how do we calculate the, how do we calculate the reward general function from this? Using this formula. So we just take the first action it took, we add this to our gamma value, multiply it by the next reward, by the next reward by the next grade of our taken action. For example, first one was like this. I mean, the reward might be 1, so it's 1. Second one might be like this, move like here, I don't know, right or wherever. The reward might be 0.5 or 2 or whatever, and it's multiplied by gamma. And in the next moves, we just move on, and as we go, our gamma is squared, or like our, how it's called in English, potanga, power, yeah, power, good, power of our gamma increases. Can you maybe someone has an intuition why it's like that? I'm just gonna ask if maybe someone knows, maybe
So
someone.
that we favor future rewards less.
Sorry.
So that we favor future rewards less.
Uh,
Less and less as time
yeah,
goes on.
yeah. Okay, cool. If someone is listening to this, something. Yeah. Fuck, it's crashed.
Does it happen? Does it happen often? That
No.
It crashes.
The problem is actually with the internet. So
It happens only when he's presenting.
it's happened when I'm connected to Adron actually all the time. Mm. I'm just gonna check real quick my camera. Is it okay?
I also had no problem with the room for like a month, and now it's just connected, no internet.
Could you explain how you designed the physics of the simulation and behavior, for example, for actuators?
It's that's why we used. Okay, I wanted to do it. I wanted to start from like zero, defining the URDF, defining the physics, the inertia, and stuff like that. But doing all of that, it takes time. It's kind of project to do.
Yeah, but for example, in the Mujoco, right? You could implement like some kind of control algorithms like PID or something else.
Yeah.
Okay.
I think it's theoretically possible. So here I'm just controlling my.
I mean,
Okay.
in other simulations are pre-built functions for this kind of algorithm.
For what do you mean, for reinforcement learning, or what you talking about?
Control engineering algorithms like PID.
Oh yeah. I don't think it's implemented in Mujoco already.
No implementation.
I don't think it's just a physics engine which you could upload your URDF files and define your.
But actuators should like behave somehow, and you have to define how you should to behave.
Yeah. So you need to define the physics. It's called the. They have the file which defines your model. It's called some.
Do you have
That
this in your
I-
code?
No. That's why I used Gymnasium, because this is already pre-built environment.
Okay.
It gives me the pendulum, all of this thing, this I don't know stick that is going on, and I'm just implementing the control function here. So I'm not doing. I really wanted to do it from zero, but when I started it, I would just maybe I would do this presentation like a month, maybe like this.
Okay, but you couldn't change the value of the damping of stiffness of the actuators in the simulation.
Here I'm not sure actually if you can do the precise changes of this pre-built model of Gymnasium, if that's what you're asking.
Okay.
You can just control it, just what I did in the code, based on some logic. The logic here is our reinforcement policy. So when you define the Mujoco file, you have like the .mgc, something like that. So that there are some converters which convert your Zacro file, your URDF file, to Mujoco file, but it's kind of messy. I tried to deal with that, but left it for some better times.
Mm. Okay.
Okay, did I answer your question? Or?
I think so.
Cool. Okay, keep rolling. Okay, so this is just, I'm gonna skip that, it's not that important. Small number for mathematical instability. When we divide by some value, we just use, instead of 0, we use that value, so our program doesn't crash. Okay, whatever. This is the vector that store our reverse function and our states in a vector, and the probabilities in a vector, so we can calculate the g of t function, our reward function. So okay, we've got the definition of our, this is the object called net. We have the policy network which we defined a second ago and stuff like that. Here we go with the optimizer. So those are just the definitions. We're actually not doing anything yet. We have the optimizer. I'm actually was wondering what it does, so I just wrote some comments here. AtomV takes those gradients calculated by reinforcement and actually changes the number in our neural network. So when we calculate all of that numbers, this omega, this omega, we need to change it. We need to apply it to our neural network. Reinforcement doesn't do that, but some AtomV algorithm does that. Yeah, that's it. Maybe someone heard about AtomV?
Yeah, so I think
Oh.
it's modification of just Adam optimization algorithm. It's like, so if you just using torch and you have this network, only this network, not entire like environment. And for example, you are training some neural network, then you can choose different optimizators.
Oh, okay. So
Yeah, and this is like one of the algorithms that is. And I'm not sure why it's Adam W. Maybe some extension or modification. Yeah, but Adam is like. I think
so that's correct. He
popular.
takes those gradients we calculated, the changes of our values, and just applies it to our neural network. Yeah. Okay. Cool. With some learning rate. Okay. So yeah, and here is simply this thing that I wrote here with the last function. Okay, so we have some sample action function, next one. Returns an action condition on a policy and observation. So in this function, we are just getting the value. Okay.
I've got another question. Is the action torque or the position controlled by the putting torque on the actuator?
You have the
Giving like position of the cards.
You. I'm not actually. The action is just a value, which adds some movement to our base. I'm not sure.
It's position, not torque.
Maybe
It's
I
like-
would say it's acceleration of the car. So in which way
No, because it's the main.
it's not torque for sure. How
Why
do
not?
you-
Why not for sure?
Why not for sure? Because we are moving the cart, and like so by torque you would mean that you have the wheels and the wheels move, or just torque like rotating.
It's
this
probably
stick.
not included.
I mean force, not torque.
Force.
Force.
Yeah, so yeah, it's probably force.
But you can like put instead of force just the position of the.
You probably could. You're using the Gymnasium library. They have some control about control method. I think, but I'm not. I didn't dive that deep, and I cannot answer your question. Can you just say, move here or move there? I think it's like applying a force to it, because it's like it sounds just logical. If we have something simulated to be like the closest to the reality, we use forces to move some things, and if you say like just teleport to this position, I'm not sure if it's gonna work, but you need
Why
to
not
check it
work?
because it's a physical environment, like it's in real environment. I mean, it doesn't sound logical to me. Maybe it works, maybe it doesn't, because I'm not sure actually about this. We can actually find it out if you wish.
Why teleport? What do you mean by that?
Because you said change the position.
Yeah, but for example, if you got like
The
classical robots in implementation, not neural networks, but for example, control engineering, you can just put command like the robots should move 1 meter ahead.
Oh,
And
that was
then
me.
algorithm can like apply.
Yeah. Okay, I get it. Yeah, I think it's possible.
Yeah, that's why I'm asking.
Okay.
What's the action actually? It's the position or the force?
Okay, I'm just gonna ask because I'm not sure. To be honest. I think it's forced applied to our base of the pendulum. Okay, we're using some.
Linear force.
Uh-huh. So what we've got here? Here's the mechanical breakdown of the moon, the actuator. Oh wait, there was it was defined somewhere here. Wait. So this is basically the site I used to get it. So you have some action space here. Like how can you act on the here's action space. You can act with the
down and you got the like whole
you
section about action space.
yeah you can just what was the question or because I misheard. So
I mean, there's a whole section about action space down there.
okay.
Is the force applied on the car?
Yeah, the force. Yeah, okay. So
And
the
the
action
resistance space, what are, could you go down a little bit? Position. The letters are a little bit too small, so could you like...
okay. The following parts in order. You can check out their documentation actually.
So it's angle for position and velocity.
Yeah. And we actually use those things from the observation of the environment to create our reward function in the code. We just you have the environment. You can just pull out some values from there and you just affect your neural network.
Yeah.
So okay, so sample action is done. So this function just does what I just described. It just plots our mean and standard deviation, and it just chooses some action from it, and it returns the value from -3 to 3 as we learned. So yeah, okay. The update is it's the thing that I told you here. So we've got some revert function, and to make it work, we need to make an iteration through it. So it's the loop describing that. So, and we do it backwards. For some reason, we take so so in our episode we have some amount of values, and we reverse them with the revert values, and we reverse them, and we calculate using these functions our output. I'm not sure if it's okay. That's how it is done, and it works. Yeah. I'm actually don't understand this part, but okay, whatever. It's just this thing that I described, nothing more. Here is the gamma value. Here is the here is our revert, right? And it changes with as we iterate. Okay. Yeah. So let's go on. Now, now let's train the policy using reinforce to master the task of inverted pendulum. Following this, following is the overview of the training procedure. This thing is actually the loop that is described in the paper called reinforce. When you have some different algorithm, they describe how to use it. So we basically implement it all. If you search for reinforce algorithm, you will find the description, like yeah, okay, yeah, like this for each episode, blah blah blah, do something, and this is basically the definition. How should we use our function? How should we deploy it? And it's deployed down there. Okay. No, wait. No, we just. Actually, I'm not sure if this is the description for each episode. Wait, I need to check it out. Yeah, okay. This will be described in the next section. So we've got our definition of the environment. So how do we do all of that thing? We just say environment equals gym make from the gymnasium. We just use the function make, and we have all of our Mujoco file, our physics included, our inertia included, all of that, and render mode, so we can see what is happening. So this thing records episode revert, whatever, total number of episodes, whatever, just for how long it will iterate. So we just, from our environment, so environment is just an object, so we can take from it some observations. So that's just what we did here. Action space of the inverted pendulum, same thing. It just gives us this -3 to 3 value that we can just move right or left or whatever. And reward over seat. Yeah, that's just writes down our reward. So seat, it basically means it's pretty high level code. So seed is basically describing our place where the pendulum will spawn every time. So okay, so I think we will see that, I mean, it trains, it works, it's better than it was, right? So we can start playing with it a bit for a bit. So yeah, if, as you can see right now, it's just, you know, oh, it's actually not that bad. But every time it starts with a different angle, so it makes our policy more realistic, more usable, because yeah, you need to include different paths it will go, so you define a good neural network to take some actions. But what if we change, just try to tell me, what if we change this seed to, like, every time when you start in the environment, just start from the same position as you did, and don't change your position. What do you think is gonna what might be the consequences of not using different values of start point? Just raise your hand at first. Hold on. Okay. So
No exploration.
no, what?
No exploration.
Yeah, that's right. It starts from the same point, and when you train your neural network, it trains on, like, oh, if you're in this point, like, move that way. Okay, it's stabilized, but and if you train it for so long, it's gonna know how to deal with that point. But if you put it into real life and say, okay, in real life, this is not gonna be the case every time, so it's gonna be, like, changing. It can be right or left or whatever. So we need to also take this into account. Okay, so yeah, here is the definition of this thing. Our agent is initialized here with our observation spaces, which we took from our environment and the action space. Okay.
We don't see that code actually.
Oh, okay. Yeah, I did wrong again. Works. Thank you. So we have defined our agent as an object. We, reinforce. We use our object space that we took from our environment here. Inherited it. So okay. So now we. This is understandable. We just, and then we have some list, which will be. Oh. Okay, there's no power. Okay, now it should. Oh, okay, now it works. And yeah, as you can see here, if you would spectate and try it on, because we use the same position every time, it trains faster actually, but worse for us because of the things that I explained. Okay, so we are just, for each episode we take some observations and info from our wrapped environment. Okay, I'm not sure what it does, but we will see probably. So we have our action equals to our agent that we defined here, sample action, this function that we have defined here, which gives us the action, which is the float number. Yeah. float number. Okay. Now so step return type is tuple, observation type, support float, okay, whatever. This represents the next observation. Oh, so this tuple represents our observation and the reward from the step. If the episode is terminated, if the episode is truncated, we just make our done true. So our episode is done when it leans too much or slides too fast. No, if it's too long. Okay, so yeah, and we get some information from our environment, like the reward, terminated, truncated info. And as you can see, we didn't define the reward itself. It's because we use some Gymnasium environment. I'm gonna, if I have time, because I need to be quick a bit. I'm gonna show you something. There's a video on YouTube where the guy just did all of this what the fuck is called? Pendulum, right? Pendulum. Inverted pendulum in real life, and he just trained, based on the physical action. That was quite impressive. Okay, so now we write our reward list, our rewards, which we generate then so this thing, and yeah. Wait, where I missed something. Wait, I missed something. Oh, it's included in our reinforced class. So at the end of every, so it's the function update. At the end of our episode, when it's done or it is terminated or truncated, agent does update, so our values in the neural network get updated. Yeah, and it's done, and then the next episode goes and stuff like that, and the new gradients come in place of old ones. Yeah, I think that's it. There's other thing that I wanted to explain, but it's not that interesting. It's quite, but I don't want to explain it. Like Q learning, we are taking into account all the things that I did before, more globally, while Q more logically changed. So, okay, I'm simply saying, maybe someone knows what is Q learning. Can you, like, simply explain what is Q learning?
Q learning is a reinforcement learning algorithm that predicts discrete output.
Yeah.
I mean, you have like finite space of the action, actually, that you could use. Yes. Yeah.
And it's just a lookup table. We have states, we have actions, and we learn by this function. We just take into account the previous, we just run the agents through some environment. It fills up the tables. It remembers, in the state 1 I took this action and I got this reward, and it goes through few times, and it doesn't use any neural network as an agent. Its agent is just changing the reward function, and based on the lookup table, it takes all of the actions. Yeah, those are the probabilities here of taking the action, or just the rewards, depends on the representation. Yeah, and that's it. Thank you for your attention. See you hopefully next week. We will talk. There would be a speaker, hopefully, which will she will describe the industry of robotics and more like soft stuff. Not, hopefully, we'll live long to see that. Okay, thank you so much. Do you have any questions?
Do you use any tricks to accelerate your computation?
No. I used the trick by deleting Windows and installing Ubuntu. That's the best, I will tell, the best decision I ever made in my life.
Is the server